All right, we're going to take a look at solving a system of three equations and three unknowns by the elimination or elimination addition method. Um, and what I'm looking at is I see all the x's in the three equations are all positive. All the y's are positive. Two out of the three z's are positive. In equation 3, the z is negative, and that may be the variable I would like to eliminate. So here's kind of the strategy here. I'm going to add equations 1 and 3 together to eliminate the z. I'm going to have to multiply equation 3 by 2, and what I'm going to be left with is an equation with just x and y. Then I'm going to go do something real similar, and I'm going to take equations 2 and 3, and I'm going to eliminate the z again. This time I'd have to multiply equation 3 by 3. And I'd have another equation with just x and y's. So then I have two new equations. I'll call them equations 4 and 5 with x and y. And it turns into something that you already know how to do. It's just this first new step of taking two combinations to eliminate the z, for instance. So here's what we're going to do. We're going to take equations 1 and 3, and I'm going to multiply equation 3 by 2, so that I'll have a negative 2z. So that's what we're going to write right here. Is we're going to take equation 1 and 2 times equation 3. So I'm just going to rewrite equation 1, and I'm going to write underneath it equation 3, and then I'm going to multiply both sides of equation 3 by 2. So equation 1 will be unchanged, but everybody in equation 3 gets multiplied by 2. And now I have what I want. I have a positive 2z added to a negative 2z, and the z's are going to cancel out, and I'll just be left with x's and y's. So 3x plus 5y is equal to 21, and I am going to call that equation 4. Okay? So that's halfway done with the new stuff. Now we're going to play the same game. I'm going to add equation 2, and I'm going to multiply equation 3 by 3. So equation 2 I'm just going to write down. Underneath it I'm going to write equation 3. And to get the z's to cancel, I need to multiply equation 3 by 3. Okay, so there's equation 2. Underneath it, we'll multiply equation 3 by 3. And you see that we have a 3z and a negative 3z, so those are going to cancel out when I add. So I'll have 4x plus 7y is equal to 29, and that's what I'm going to call equation 5. Okay, so now that's all the new stuff. Now it turns into just a system of two equations and two unknowns. So I've labeled my equations 4 and 5, and we're going to go ahead and eliminate the x here. LCM of 5 and 7 is 35, so that's going to require a sort of larger number. LCM of 3 and 4 is 12, so that's a little bit smaller. So we're going to eliminate the x. One of the x's has to be negative, one has to be positive. I'm going to go ahead and make the x in equation 4 negative. So in order to make this 3 here, in order to make it a negative 4, I mean a negative 12, I have to multiply by negative 4. So we're going to multiply equation 4 by negative 4, and then we're going to add equation 5 to it, but we need to multiply equation 5 by 3. So I'm just going to write down equation 4, 3x plus 5y equals 21. And then underneath it, equation 5, 4x plus 7y equals 29. Okay? And we want a negative 12x in equation 1 and a 12x in equation 4, equation 5. So we want this to be a negative 12 and this to be a positive 12. So when I add them, they're going to drop out. So we're going to multiply the top equation by a negative 4. Negative 12x minus 20y equals negative 84. And then we're going to multiply the bottom equation by 3. 12x plus 21y equals 87. We're going to add straight down. And lucky for us, we just get regular old y, or 1y equals 3. So that's good. Now, just like before, you can substitute y back into either equations 4 or 5. I'm going to go with equation 4 because it's a little bit smaller numbers. And 3x plus 5 times y, but y is 3, so it would be 5 times 3 equals 21. We're going to solve for x, so we're going to isolate it. So subtract 15. So 3x is equal to 6. Divide both sides by 3. X is equal to 2. And now we go back to one of the original 3. It does not matter which of the original 3 it is. It's just we have to go back to one of them. So I'm going to do equation 1 since it looks like it's the simplest. So x plus y plus 2z equals 11. The x is 2, the y is 3, plus 2z equals 11, and we're trying to isolate the z. So we have 5 plus 2z equals 11. We'll go ahead and subtract 5 from both sides. So 2z is equal to 6. Divide both sides by 2. Z is equal to 3. And this time my ordered triplet is 2, 3, 3. And if I go back and check to see if this works in all 3 equations, if x was 2, then we'd have a 2 here. The y is 3, and then the z is also 3. So 2 times 3 would be 6. So 2 plus 3 is 5 plus 6. That's 11. That looks good. And then the next one, x is 2, y is 3, z is 3. 3 times 3 is 9. 2 plus 3 is 5, plus 9 is 14. Works in that one. And the last one, x is 2, y is 3, times 2 is 6, z is 3. 2 plus 6 is 8, minus 3 is 5. Works in that one. So happy times, it works in all 3 equations. So there's a lot of details going on here, and I try to think about what I'm doing. Okay, I'm going to take 2 combinations of the 3 originals, and I'm going to eliminate the z. What I'm left with is a system of 2 equations and 2 unknowns. That's the 4 and the 5. So then it's kind of its own new problem that I know how to solve by elimination method. I eliminate one of the variables. I eliminated the x in this case. I find my y. Once I find my y, I can go back and find my x. Once I find the x, then we can go back and find the z, and then check our solution. So there's a lot of steps involved. Try to just get a general picture of what you're doing, and then you go with what you need to do in the problem. So it just takes some experience.